Hey everyone, and welcome back to the channel. If you're a Java developer, you know there's one interview topic that can make even seasoned pros a little nervous: multithreading. It's complex, it's tricky, and getting it wrong in the real world can cause disastrous bugs. That's why interviewers love to ask about it. Let's start with the absolute basics. Can you explain the difference between a process and a thread?
Absolutely. Think of a restaurant. The entire restaurant is a process. It has its own building, its own kitchen, its own staff. It's a self-contained operation with its own dedicated resources, like memory space. Now, inside that restaurant, you have several chefs. Each chef is a thread. They all work within the same kitchen, sharing the same stove, the same ingredients, and the same refrigerator. So, a process is an independent program with its own isolated memory. Threads are the individual workers inside that process. They are lightweight and share memory, which makes communication between them fast. But it also means if one chef makes a mess, a bug, it can affect the entire kitchen.
Okay, good. Let's move on to thread safety. A classic question: when would you choose to use a re-entrant lock over the standard synchronized keyword?
Great question. For simple cases, synchronized is fine. It's easy and clean. But you reach for a re-entrant lock when you need more power and control. There are three main reasons. 1. Interruptible locking. A thread waiting for a re-entrant lock can be interrupted if another task takes priority. A thread waiting on a synchronized lock is stuck there until it gets the lock, period. 2. Timed waits. You can have a thread try to get a lock for a specific amount of time, say 50 milliseconds, and then give up if it can't. This is a powerful way to prevent deadlocks. Synchronized can't do this. It waits forever. And 3, fairness. You can configure a re-entrant lock to be fair, meaning it gives the lock to the longest waiting thread. This prevents a situation called starvation, where some threads never get a chance to run.
Let's talk about problems. What is a deadlock? And more importantly, how do you prevent it?
A deadlock is a situation where two or more threads are blocked forever, each waiting for the other to release a resource. Imagine two threads, thread A and thread B, and two locks, lock 1 and lock 2. Thread A acquires lock 1. At the same time, thread B acquires lock 2. Now, thread A tries to get lock 2, but it's held by thread B, so it waits. And thread B tries to get lock 1, but it's held by thread A, so it waits. They're now stuck in a deadly embrace, and neither can ever proceed. The best way to prevent this is to break one of the conditions required for a deadlock. The easiest one to enforce is lock ordering. You establish a fixed order for acquiring locks throughout your application. For example, if you need both lock 1 and lock 2, you always have to acquire lock 1 before lock 2. This makes a circular wait impossible.
Modern Java provides high-level tools to handle these issues. Let's test your knowledge of them. Scenario time. Your application needs to wait for 3 different services: a database, a messaging queue, and a cache to initialize before it can start processing requests. Which tool from java.util.concurrent do you use?
That's a perfect use case for a countdown latch. You initialize it with a count of 3. Each of the 3 services runs in its own thread. When a service finishes its initialization, it calls the countdown method on the latch. Meanwhile, your main application thread calls latch.await. This method blocks and simply waits until the count reaches 0. Once the third service calls countdown, the latch's count becomes 0, the await method unblocks, and the main application can proceed safely, knowing everything is ready.
Let's talk collections. Why is concurrent hash map so much more performant than a simple collections.synchronized map?
It comes down to one key idea: lock striping. A synchronized map is simple. It puts one giant lock on the entire map. If any thread wants to read or write, it has to acquire that single lock. If you have 16 threads trying to access the map, 15 of them are waiting at any given time. It creates a massive bottleneck. Concurrent hash map is much smarter. It doesn't have one big lock. Instead, it divides the map into multiple segments or buckets, and each segment has its own lock. So thread A can be writing to bucket 5. At the exact same time, thread B is writing to bucket 12. They don't interfere with each other. This allows for a very high degree of concurrency and is why it's the go-to choice for multi-threaded maps.
Final question, a subtle but critical one. When implementing a thread-safe singleton using the double-checked locking pattern, why must the instance variable be declared as volatile?
This is a fantastic question because it gets to the heart of the Java memory model. Without volatile, your code can break in a very sneaky way due to instruction reordering. When you create a new object, instance equals new singleton, it's not one single step, it's actually 3. Allocate memory for the object, initialize the object's fields, run the constructor, assign the memory address to the instance variable. The problem is the Java compiler or CPU can reorder steps 2 and 3 for performance. So a thread could see the instance variable as not null. Step 3 happened. Before the object is fully initialized, step 2 is still pending. It would then return a half-constructed, buggy object. Declaring the variable as volatile prevents this reordering. It creates a happens before guarantee, ensuring that any thread that sees the instance as not null will also see the fully initialized object. If you can explain the why, you'll prove you're not just a coder, you're a problem solver. If you found this video helpful, hit that like button, subscribe for more deep dives into Java development, and drop a comment below with a topic you want us to cover next.